Hello, and in this second video about diodes, we'll be looking once again at the PN junction and seeing how the characteristic properties of the diode arise. We'll also be introducing Shockley's equation, which describes the relationship between the current through a diode and the voltage across it. You may remember this animation from before. If we have a PN junction here with a p-type material on this side with a few vacant states at the top of the valence band, and an n-type material on this side with a few mobile electrons at the bottom of the conduction band, and we put these two blocks of semiconductor together and let them achieve equilibrium, then some of the mobile electrons at the bottom of the conduction band in the n-type material will drop down and fill some of the vacant states at the top of the valence band in the p-type material. This leaves this region of the semiconductor here with a net positive charge, since it's just lost an electron, which means it attracts electrons. Electrons don't need as much energy to get to these states, so these states drop in energy. This side of the junction, however, the p-type material, now has a net negative charge, so it is repelling electrons. You have to do more work to get electrons into these states, so these states rise in energy. Equilibrium is reached when the electrons from the n-type can no longer lose energy by moving to the p-type material because the p-type states have increased in energy. Now, if I put an external field across this junction in this direction, so the electrons are trying to flow this way from left to right, then this would happen. We'd get some more electrons leaving the n-type material here, being attracted to the source of the electric field, and we'd get more electrons moving into the valence band in the p-type material here, again being attracted by the externally applied electric field. And then you'd reach this state where nothing more can move, because there are no mobile electrons left in the conduction band and no free states left for electrons to move into in the valence band. So no current flows. However, if we put the electric field, an external electric field, on in the other direction, we can get to this state where electrons are coming in from the n-type material here off the screen, being attracted in this direction. They arrive at the junction or near the junction, drop down into the vacant states in the p-type material, and the electrons can happily leave via these vacant states in the p-type material and carry on through the circuit. So we can get quite easily a current flowing in this direction, from left to right. This of course means that the electrons are flowing from right to left. Now, according to this animation, if I put the electric field on in the other direction, the direction in which current cannot flow, then after the electrons leave the conduction band and fill up all available states in the valence band, no current at all is flowing. But I said in a previous video that there is a very small current that does flow when the diode is reverse biased. And you can understand how that current is flowing if you think about the bands in terms of the Fermi-Dirac probability distribution. This is a diagram of the energy states of a reverse biased PN junction, with the conduction band up here and the valence band down here. Now, I've plotted the probability of occupancy given by the Fermi-Dirac equation as these red dotted lines in both the p-type material, the n-type material, and at the junction itself. And you'll see that at the junction itself, the probability distribution starts off, as you might expect, at around 1 at the bottom of the valence states, and goes up to about 0 at the top of the conduction band. However, right about in the middle of the junction there, the Fermi level is halfway between the top of the valence band and the bottom of the conduction band. If we just think about what that means, we've got the bottom of the conduction band doing this, and the top of the valence band doing this. This is energy, and this is distance through the p-n junction. Consider this point around about there, where the Fermi level is halfway between the two states. Now, in the animation, we showed this case as having no mobile electrons in the conduction band and no free states in the valence band. However, the probability that there is an electron in the conduction band, in this case, is not absolutely zero, but it is something that would be very close to zero. But it's that little difference between its actual value and zero which allows a very small reverse current to flow. The Fermi-Dirac distribution says that the probability that a state is occupied is given by 1 over e to the power of the energy of that state minus the Fermi level divided by kT plus 1. Now, for a typical silicon diode, the gap between the conduction band and the valence band is about 0.7 electron volts. If you remember, an electron volt is a unit of energy equal to the amount of energy that it would take to move 1 electron through 1 volt. This means an electron volt is 1.6 times 10 to the power of minus 19 joules. So if we consider this point here, where the Fermi level is halfway between the conduction band and the valence band, then the gap between the Fermi level and the energy at the bottom of the conduction band would be half of 0.7 electron volts, or about 0.35 electron volts. And this formula would allow us to calculate the probability that these states in the conduction band are occupied. The answer would be 1 over e to the power of e minus the Fermi level, 0.35 electron volts, 0.35 times 1.6 times 10 to the power of minus 20, 10 to the power of minus 19 rather, divided by k times t. K is the Boltzmann constant, 1.38 times 10 to the power of minus 23. T is the temperature in Kelvin, so at typical room temperatures that would be times 290, and there's a plus 1 on the end, which in most cases like this doesn't make a lot of difference, but I'll put it in there anyway. Now, what would that be equal to in this case? And the answer is just a little bit under 1 in a million. So just a little bit under 1 in a million of these possible states here would actually be occupied. That's not a huge number, but it's enough to allow a very small current to flow. What's happening is that there is a probability that some of these states in the valence band are empty, and some of these conduction states in the conduction band are full, and it allows a very small number of electrons to jump up there, just due to the thermal energy that they have, and carry on out of the p-n junction. So there's a very small amount of current that flows. And the amount of current that flows is determined by the probability that an electron has enough thermal energy, just due to its temperature, to jump up from the valence band to the conduction band. And that's a function of how far the conduction and the valence band are apart. It's not a function of what the electric field strength is or the voltage across the diode is. So for almost any case of reverse bias, almost any reverse voltage across the diode, approximately the same current will flow. And this is called the saturation current. A more careful analysis leads to the Shockley equation, which is the general equation for a diode which relates the current flowing through it to the voltage across it. And this is it. The current through the diode is this saturation current, which is the current that flows when the reverse voltage is across the diode, times e to the power of the charge on an electron times the voltage across the diode over kT minus 1. And there's a factor of n that's usually put in there as well. N is called the ideality factor. It's for an ideal diode, it would be equal to 1. But due to manufacturing imperfections, for real diodes, n is typically somewhere between 1 and 2. You can confirm that IS, the saturation current, is the current that flows when there's a reverse bias across the diode by noting that if V is a negative number, then we would end up, say it's minus a volt or something, then we would end up here with e to the power of minus 1 minus a volt divided by n times, well, so happens that at about room temperature, the Boltzmann constant times the temperature divided by the charge on an electron is approximately 25 millivolts. So 25 millivolts minus 1. When n is equal to 1, that would be e to the power of minus 40 minus 1. Well, e to the power of minus 40 is negligibly tiny compared to 1, so the net result would be, to a very good approximation, minus the saturation current would be flowing. And if the voltage across the diode is more negative than 1 volt, this would be even more negligible, and we'd still have the saturation current flowing. If you plot this on a graph, you'll find that the current flowing through a diode against the voltage across it is effectively tiny, just equal to the saturation current, until you get to a few tens of millivolts away from zero. When the voltage across the diode is 0, then the current through the diode is 0. You just have e to the power of 0, which is 1 minus 1 of 0. So this goes through the origin. And then it starts to go up exponentially like that. And we'll get typical diode characteristics that look like that. Next time, we'll see how accurate this type of sketch is, and have a look at Zener diodes as well.